After creating the model in the part module and assigning material properties in the property module, all parts must be assembled in one similar coordinate system, because the components in the assembly module can be analyzed. For clarification, I create two parts called Part 18 and Part 19, which have vertical faces. In the assembly module, from Create Instance, choose Parts. When you create a part instance, you can choose to create either a dependent part or an independent. A dependent instance shares the geometry and the mesh of the original part. As a result, you can mesh the original part. The advantages of dependent part instances are that they consume fewer memory resources. In contrast, for the independent part instance, you cannot mesh the part from which you created an independent part instance, as it is a copy of the geometry of the original part. For complex models with different mesh sizes, you can move the nodes of the original meshed part, and your modifications appear on all dependent instances of the part. You can use the model tree to determine if an instance is dependent or independent as follows. And if you want to exclude part from the analysis, select Exclude from Simulation. Similarly, you can include part instances that were previously excluded by selecting Include in Simulation. In the assembly module, the components are assembled, and each part instance has its own position within the assembly, not anything else. For example, if we put these two shapes on top of each other and apply pressure, there will be no interaction between them. For constraining two instances with parallel planar faces, select Constraint Parallel Face from the main menu bar. To apply a constraint that positions a movable instance so that a selected face is parallel to a selected face of a fixed instance. Parallel face, face-to-face, and the parallel edge is usable for 3D models. Edge-to-edge option can be used for both 2D and 3D models. Another option like Create Constraint Coaxial, Create Constraint Coincident Point, and Create Constraint Parallel CSYS are usable for 1D, 2D, and 3D models. Parallel CSYS applies a constraint that positions a movable instance so that a selected datum coordinate system is parallel to a selected one of a fixed instance. Select Constraint Parallel Face to apply a constraint that positions a movable instance so that a selected face is parallel to a selected face of a fixed instance. For example, we parallel these two faces as follows. Face-to-face applies a constraint that positions a movable instance so that a selected face is parallel to with a specified distance away from a face of a fixed instance. created a distance of 10 meters between these two faces by this tool. Parallel edge tool applies a constraint that positions a movable instance so that the selected edge is parallel to a desired edge of a fixed instance. The coaxial position constraint causes a selected cylindrical or conical face of the movable instance to have a common axis with a selected cylindrical or conical face of the fixed instance. The coincident point constraint causes a selected point on the movable instance to coincide with a selected point on the fixed instance. With Instance Translate tool from the main menu bar, move selected part or model instances along a selected vector. Select the part or model instances to translate. Then select the start point of the translation vector. After that, select the end point, as you can see here. Use Instance Rotate tool to rotate selected parts or model instances about a selected axis. First, select the part instances to rotate, then select the start and end point of the vector, which defines the axis of rotation. You can select any existing vertices or datum points. Or you can enter the coordinates in the text box. Then enter the rotation angle. For example, if you consider the z-axis as the rotation axis, enter the first point 0, 0, 0 and the second point on the z-axis like 0, 0, 0, 0.1. Select Instance Linear Pattern from the main menu bar to create multiple copies of a selected part instance in a linear pattern. To explain this option, I would rather delete the part. First, select the part instances that you want to copy. You can create a pattern that extends in one direction, horizontally or vertically, or in two directions. Click the arrow to the right of number to increase or decrease the number of copies to create, including the selected instances. This is a small part of the Abaqus for Beginners training package. There is a lot more valuable information in other parts of this package that you can get on our website. We suggest you do your project by saving your time and getting basic in training so that you don't get tired of Abaqus errors. A radial pattern positions the new instances in a circular pattern. You can specify the number of instances and determine the angle between the first and last copy. To merge a selected group of part instances, select Merge Cut Instances tool. In order to merge the parts, they must be in contact with each other. For this reason, we translate this part. Enter the name of the part that will be created by the operation, then select the type of operation. Any native or orphan mesh nodes and elements are not included in the new part to merge the geometry of part instances. To cut part instances, choose Cut Geometry. By default, Abaqus removes the intersecting boundaries between instances. If you want to retain the intersecting boundaries, choose Retain from the bottom of the Merge Cut Instances dialog box. The effect of removing the boundaries is shown in this example. For the cut operation, parts must be connected because the cutting geometry must touch or overlap the geometry of the part instance to be cut. If you chose a cut operation, do the following. Select the geometry of the part instance to be cut, then select the part instances that will make the cut. Suppress can suppress the original part instances but retain them in the model database. Here, choose Delete to delete the original part instances from the model database. You can enter the step module at any time during the analysis by clicking Step in the module list located in the context bar. You can use the step module to create and define the analysis steps and associated output requests. Abaqus creates a certain initial step at the beginning of the model's step sequence and names it initial, and it cannot be renamed, edited, replaced, copied, or deleted. When you select Create Step from the main menu bar, a Create a Step dialog box appears in which you can specify the procedure type for the step that you are creating. General analysis steps can be used to analyze the linear or nonlinear responses, and linear perturbation can be used only to analyze linear problems. A static general procedure is one of the most usable solvers in which inertia effects are neglected and ignores time-dependent material effects. In the time period field, enter the time period of the step. If toggle on the nonlinear geometry or NLGeom, Abaqus indicates a count for geometric nonlinearity during the step. If you choose automatic type, you can enter the upper limit to the number of increments in the step in the maximum number of increments field. After that, enter values for increment size in the maximum, minimum, and initial fields. If fixed time incrementation is used, Abaqus will not check that the computed response is stable during the step or not. In the Other tab, we can define the equation solver, solution technique, and the settings associated with them. The analysis procedure can be changed from step to step. The second type of analysis can be static, RIX, which is for nonlinear static problems including nonlinear buckling, as well as displacement force response leads to a negative stiffness, and also the strain energy is released from the material. Another step is dynamic explicit, which is used mostly in large models. Models have a discontinuity or in nonlinear analysis. The explicit dynamics procedure performs a large number of small time increments efficiently. This option is used to control uncoupled heat transfer for either transient or steady-state response, conduction, convection, or radiation. A direct integration dynamic analysis in Abaqus must be used when studying nonlinear dynamic responses, or can be based on the modes of the linear system. Coupled temp displacement is used to analyze problems where the simultaneous solution of the temperature and stress displacement fields is necessary. For example, in forming problems when too much heat changes the shape of the material in an elastic state. Coupled thermoelectrical problems are those in which coupling between the electrical potential and temperature fields, making it necessary to solve both fields simultaneously. A cyclic analysis is a quasi-static analysis that uses a combination of Fourier series and time integration of the nonlinear material behavior to obtain the stabilized cyclic responses of the structure iteratively. The cyclic analysis is ideally suited for substantial problems in which many load cycles must be applied to obtain the stabilized response if the transient analysis is performed. Use dynamic temp disp explicit procedure when the stress analysis is dependent on the temperature distribution and the temperature distribution depends on the stress solution. Geostatic stress is used to verify that the initial geostatic stress field is in equilibrium with applied loads and boundary conditions and to iterate if necessary to obtain equilibrium. Mass diffusion analysis provides the modeling of the transient or steady-state diffusion of one material through another. For example, modeling the diffusion of hydrogen through a metal. SOIs are used to specify transient or consolidation or steady-state response analysis of partially or fully saturated fluid filled porous media. Visco is used to obtain a transient static response in analysis with time-dependent material behavior like creep, swelling, and viscoelasticity. This option is valid until the inertia changes can be ignored. A linear perturbation analysis step is a step in which you activate a perturbation procedure that determines the response about a base state due to perturbation loads and boundary conditions. The buckle is used to control eigenvalue buckling estimation. Frequency is used to perform eigenvalue extraction to calculate the natural frequencies. In the static linear perturbation procedure, by freezing contact status, the contact contributions and thereby the overall governing equations are imposed to be linear in the solution variables and result in a purely linear static perturbation analysis. The steady-state dynamic analysis provides the steady-state amplitude and phase of the response of a system due to harmonic excitation at a given frequency. Substructures are defined using the substructure generation procedure. Multiple substructures can be generated in an analysis. For example, you will create a new field and history output by creating a step like static general and accepting all defaults. The field and history output are initially available in the output database and are limited to those variables you have saved during the analysis. You can increase these analysis results by operating on field output to create new results for the whole model or part of it. Select every n increments to request that Abaqus write field data to the output database in increments. You can then specify the number of increments in the n field that appears. In this section, you must activate any variables needed to see graphically or as a contour in the results section. For example, you must enable the level set value phi option to analyze a crack. You can also create other outputs. History output is created by default that can be edited like the previous section. The difference between field and history output is that you can display history output using XY plots. This is a small part of the Abaqus for Beginners training package. There is a lot more valuable information in other parts of this package that you can get on our website. We suggest you do your project by saving your time and getting basic in training so that you don't get tired of Abaqus errors.